In experiment 15, we are going to graphically determine the values of the standard enthalpy change and the standard entropy change for a chemical reaction. The three thermodynamic functions we've learned in this particular chapter shows the relationship between the standard free energy change of a reaction, the standard enthalpy change, and the standard entropy change, that's delta G naught equals delta H naught minus T delta S naught. Of these three thermodynamic functions, the delta H naught and the delta S naught are constants over a wide temperature range, but the delta G naught is not. It actually is affected by temperature, and we're going to use that to our advantage today to calculate what the standard enthalpy change is and what the standard entropy change is for a chemical reaction. If I take this thermodynamic equation and divide it by T, my relationship will look like this. The last term, negative T delta S over T, will have the T's cancel out, so we wind up having delta G naught over T equals delta H naught over T minus delta S naught. For that middle term there, if I separate it into delta H naught multiplied by 1 over T, you should be able to recognize the form of this equation. This is y equals mx plus b. This means that if you were to plot delta G naught over T versus 1 over T for a particular chemical reaction, we can determine graphically the standard enthalpy change and the standard entropy change. The slope is going to be the standard enthalpy change, and then the y-intercept is going to be the negative of the standard entropy change. The way we're going to do this is we're going to have to come up with a way to calculate what delta G naught is for a chemical reaction at multiple temperatures. And it turns out the delta G naught for any chemical process can be determined from its equilibrium constants. If we can calculate the equilibrium constants at various temperatures, we can calculate the standard free energy changes at various temperatures, and this will be done with the relationship delta G naught equals negative RT multiplied by the natural log of the KEQ. So in today's lab, we're going to try to calculate equilibrium constants at different temperatures. The type of equilibrium constant we're going to be determining today is a KSP. So I'm going to do a different salt than you're going to do in the lab today, but let's say we want to calculate the KSP for potassium chloride at 2 different temperatures. You're going to be using potassium nitrate today, and you're going to be doing this at 3 different temperatures, but the technique will be the same. If we take a mass of potassium chloride and dissolve it in as much water as we can, then we can actually, if we have the measured mass of KCl, we can calculate how many moles of KCl there are. Now at room temperature water, the amount of water we're going to use is not going to allow all the potassium chloride to dissolve. So we're going to have a solution that looks like this. In order to get it to all dissolve, we're going to place it into a water bath with hot water in it. That hot water is going to heat it up, it's going to dissolve the solid, and then we're going to take the heat away and we're going to let the solution cool. So once it's all dissolved, it'll look like this. As it cools, eventually it's going to reach a point where the potassium chloride just barely starts to crystallize out. And as soon as you see crystals in there, you record the temperature, because that's the temperature where the solution was perfectly saturated and just started to crystallize out. If you measure the volume of water now at this particular temperature, you can calculate the molarity of the potassium chloride in this saturated solution at this first temperature. Now, after that, we're going to add some more water, and we're going to heat it up, and then we're going to let it cool. So by adding more water and heating up the solution, you'll redissolve the potassium chloride. Taking the heat away, we let it cool down, and you just watch for the first crystals to appear. And once those first crystals appear, you record the temperature again. Now that we know the temperature, we measure the volume, and then moles divided by volume will give us molarity. So the molarity is going to be calculated for the saturated solution at this second temperature. So if we now know the molarity of the KCl, because it's a 1-to-1-to-1 ratio, that'll actually be the molarity of the potassium ions and the molarity of the chloride ions in these saturated solutions. So at our first temperature, the KSP will just be the known molarity of potassium ions multiplied by the known molarity of chloride ions, whatever those are, that'll be the KSP. At the second temperature, because the molarities will be different, the KSP will be these different known molarities. We multiply those together, and we'll now have the KSP for potassium chloride at 2 different temperatures. That's going to allow us now, and let me give you the data, let's say at 298, the KSP was calculated to be 3.0 times 10 to the second, and at 348, it was calculated to be 8.0 times 10 to the fourth. If we want to calculate the standard enthalpy change and the standard entropy change for the reaction, we can now do this graphically. But we first have to calculate the standard free energy changes. So those will be negative RT multiplied by the natural log of the equilibrium constant. So for my first temperature of 298, I'll go negative R multiplied by 298, multiplied by the natural logarithm of that corresponding KSP, which is 3.0 times 10 to the second. This multiplies out, and because the KSP in my example is two significant figures, I'll get a two significant figure answer. My delta G naught at temperature 1 is negative 14,000 joules. So we now know the delta G naught that's associated with the temperature 298. At the higher temperature, we'll put in the temperature of 348, its equilibrium constant 8.0 times 10 to the fourth, and we calculate delta G naught at our higher temperature. It comes out negative 33,000 joules, or negative 32,664 if you keep the guard digits. So we now have our second delta G naught, that should actually say delta G naught 2 up there instead, at our second temperature of 348. So with these, now we can actually make a graph, and you're going to wind up doing this on Excel. So on Excel, to make this graph, the x-axis is 1 over t, the y-axis is delta G naught over t, so you have to put the columns in that order, the x values first, the y values second. So our 1 over t column can be calculated in Excel by going equals 1 divided by 298, and the 1 over 348 can be calculated by going equals 1 over 348. I've actually already just calculated delta G naught over t here by taking my delta G naught value, dividing it by t. So at the lower temperature, I get negative 47 kilojoules per Kelvin, and at the higher temperature, negative 93 kilojoules per Kelvin. When you select those points and create the graph and ask it to draw a line and give you the equation, the results will look like this, and they give us the equation for the line. From this equation, whatever the slope is, that's going to be your standard enthalpy change for the reaction, which comes out 96,381 joules, or going back to our two significant figure KSP value, 96,000 joules as the standard enthalpy change. The negative of the y-intercept will be your value for delta S naught. So the negative of our intercept is positive 370.82 joules per Kelvin. And then keeping two significant figures, that would be reported as 370 joules per Kelvin. So for this particular reaction, we've now graphically determined its standard enthalpy change and its standard entropy change.